Hello, good morning. Myself, Dr. Shaila Dinkar Apte. Today, we'll be discussing FIR Filter Design. This is the book published by me, Digital Signal Processing. This is published by Wiley India Publication, and it is the second edition of the book. So, you can refer to the book. You will get all contents that I am speaking in this particular video. So firstly, we'll understand what is a DT filter. DT filter means discrete time filter. We'll be designing discrete time filter, and then we'll be digitizing the filter coefficients to get the digital filter. Now, the system that will modify the spectral contents of the input signal will be called as the filter. So, filtering is the filtering of the spectral contents. Depending upon the nature of the impulse response, we call it as FIR filter or IR filter. So, when the impulse is applied as input to the filter, the response may last for finite duration or the response may last for infinite duration. If the impulse response is persisting only for a finite duration, we call it as a FIR filter. If the response extends up to infinity, it will be called as IR filter. Now, ideally, the filter response requirements, those are specified by the user. They are specified in the frequency domain, and it is, suppose we consider the specifications of the low pass filter, then it is specified as a brick wall filter, and the specifications are h omega is equal to 1 for the frequencies between minus omega to plus omega c, where omega c is the cutoff frequency, and above omega c up to pi it will be equal to 0. So let us see how it looks like. So the frequency response that is specified in frequency domain, we say that it is periodic with period equal to 2 pi. That means it is existing between minus pi to plus pi, and it is periodic with period of 2 pi. So we can easily extend it on either side to make it periodic in the frequency domain. Now, why at all we want to have frequency domain periodicity? This is because we want to design a discrete time filter. And if I want to get discrete time signal as the time domain signal back, when we go to frequency domain, we must have the periodic waveform. That is the periodic frequency response. So what we do is, see, when we have the analog signal and when we are sampling it, we can only sample it provided the signal is of finite bandwidth. So even if only if the signal is band limited, I can sample it with a sampling frequency of twice W, right? And this bandwidth W, if I want to represent it in terms of angular frequency, it will be equal to pi, because the Nyquist frequency will be equal to W. When Fs is 2W, Nyquist frequency will be W, and in terms of angular frequency, it will be represented as pi. So the frequency response will be specified between minus pi to plus pi, and hence it will have a period of 2 pi, and when we can replicate it on either side and we can represent it as a replicated spectrum, then we can take it in the time domain, and in the time domain we will get the filter response as the discrete time signal. That is the requirement. This is because we want to design the discrete time filter. Now, inverse transform of the ideal filter response. See, Hn is given as existing between minus omega c to plus omega c, e raised to j omega and d omega. This is 1 upon 2 pi. So we are taking the inverse transform. That is why this 1 upon 2 pi appears. So Hn is 1 upon 2 pi. Now when I integrate this, 1 upon j n e raised to j omega n minus omega c to plus omega c. Now if you solve this, you will get it as omega c upon pi sine omega c n upon omega c n, where the sine omega c n upon omega c n is a sinc function. This is existing for n not equal to 0, and for n equal to 0 it will be omega upon pi, because sine 0 upon 0 is equal to sine theta upon theta tends to 1 when theta tends to 0. Now what are the difficulties in the design of brick wall filter? The difficulties are the system response that we get will include infinite coefficient. So when I take the inverse of the inverse Fourier transform of the brick wall response, I'll be getting a sinc function which will be existing between minus infinity to plus infinity. So the filter has infinite coefficients, and that is the hurdle. Second hurdle is the response exists for negative values of n also, and hence it becomes non-causal. So in order that the system becomes implementable, the system will have to be, the filter response will have to be causal. So we can make it causal actually by just shifting it. So that will come to it later on. So we can conclude that the design of ideal brick wall filter will not be possible. Why? Because there will be requiring infinite coefficients, and the filter response that we get is non-causal. So we'll have to make some changes in it so that it will become implementable. Now what we can do is we can make the number of coefficients in the filter response as finite and then make it causal. So these two things are required. Firstly, we'll have to make it finite and we'll have to make it causal, and then the FIR filter response that we get will be approximating the frequency response specifications those are given by the user. Now, by truncating it and making it causal, it is possible that we get the filter response which closely approximates the filter response specifications. This is what is called as Paley-Wiener theorem. So this is exactly the meaning of the Paley-Wiener theorem. Now let us see what is Fourier series expansion method. Note that the name of the method is slightly confusing. Why? Because we write down the Fourier series expansion for the periodic signal in time domain. Now here the signal is periodic in frequency domain, and we are trying to represent it as a Fourier series in time domain. So in this case, frequency and time, these particular names are interchanged, but we'll be getting the same result. So there is no harm in using the word as Fourier series expansion. So it is customarily called as Fourier series expansion method only. And see, the ideal response that is specified is between minus omega c to plus omega c, and above omega c up to pi and minus omega c up to pi, it is equal to 0. Now what I have done is I have replicated this response on either side, that is around 2 pi, around minus 2 pi. It will also be replicated at 4 pi, 6 pi, and then at minus 4 pi, minus 6 pi, etc. So this is a replicated response that is represented. Why I have replicated it? Because I want to get the discrete time response in time domain. Now I have written this as angular frequency. Angular frequency here is written as pi. Now, if I want to represent it as normalized frequency, this pi is representing the Nyquist frequency. So, normalized frequency will be Fn upon Fn, so it will be equal to 1 in this case. So, normalized frequency response will be represented between minus 1 to plus 1, right? And it will be replicated around 2, 4, 6 and so on. Here minus 2, minus 4, minus 6, etc. Now let us see how the filter calculations will be, filter design will be done. Now we try to write this j omega n. J omega n is j 2 pi fn, where f is the corresponding frequency. Now this f frequency, I am writing it as digital frequency, I am writing it as analog frequency divided by the sampling frequency. What is sampling frequency? It is twice the Nyquist frequency. So these two will cancel and I'll get j pi fn upon the corresponding f, analog frequency, divided by fn. F upon fn is nothing but the normalized frequency. I represent it by the letter nu. So it is j n pi nu. Now how to calculate the corresponding filter coefficients? It will be 1 upon 2 integration minus 1 to 1. Now here pi will vanish because I am writing the normalized frequency. HD nu e raised to minus j n pi nu d nu. This is the equation for calculation of filter coefficients. And then I calculate the group delay as minus dd nu of the phase. We will consider this in detail further. Now this Cn I can further write it as 0 to n because it is symmetric. It is represented as 0 to 1 and it will be twice. So these two will be getting cancelled. E raised to hd nu. This is g raised to j n pi nu plus e raised to Jn pi nu divided by these two, so it will give you the cost function. And the cost is symmetrical function. Cost function is symmetrical, so I can represent it as the cost function, and I can evaluate these coefficients as Cn. Let us go ahead and do it. Now, the ideal filter response that I get. So, if I represent the frequency domain response as a brick wall filter, why it is called as brick wall? Because it just looks like a brick. It is existing between minus omega to plus omega, and above that it is zero. So if I take the inverse Fourier transform, I'll be getting a sinc function that we have seen. And this function, how it is varying between 0 to infinity on one side and 0 to minus infinity on the other side. This is the ideal thing. Now to get the finite impulse response, what I'll have to do? To make the impulse response finite, we need to truncate it. Let us truncate it and use only the coefficients between some finite minus q to plus q. Now you will have to select this q. How to select this q? You will have to select this q so that energy above q and energy below minus q is very small and negligible as compared to the energy between minus q to plus q, so that the truncation becomes justifiable. Otherwise, you cannot truncate it. When you truncate, you will have to say that the energy that I am discarding above plus q and minus q is very, very small. So I can discard. Now, when Q is properly selected, the frequency response can be obtained using the coefficients between minus Q to plus Q, and it will be giving you the approximated desired response. So we can write this as it is approximately equal to, because this tilde is there, and this indicates that it is the approximated response minus Q to plus Q Cn e raised to j n pi. So this is the response. Now we'll have to make it causal. Now here the coefficients are between minus q to plus q. So you introduce a delay of q samples. So whatever C of minus q, you make it as a0. C of 0, you make it as a of q plus 1, and the corresponding CQ, you make it as a of 2q. So if you write it in terms of the a coefficients, these a coefficients will vary between 0 to 2q, and the center coefficient will be the coefficient q, and then it will be symmetrical on either side. Right. Now, even though it is symmetrical, when we introduce the delay of q samples, it will be symmetrical around q now rather than 0. Now, what will be the filter properties? The filter will have 2q plus 1 coefficients, because q on left hand side, that is negative side, q on positive side, and the center 0 coefficient. The impulse response will be symmetric with respect to AQ now, because when we are shifting, we are introducing a delay of Q samples. AQ will be the center value. The duration of the response will be 2Q into T, sampling frequency. This is the sampling time interval. T is the sampling time interval where T is equal to 1 upon Fs. So we can calculate actually what will be the response of the filter. So this is a finite impulse response filter. So what is the finite response? Finite duration that you can calculate. And it introduces a phase change for every sample equal to minus n pi nu. There is q pi nu. When we introduce a delay of q samples, the delay of q pi nu will be introduced for every sample. So as I increase the value of frequency, the corresponding phase also linearly increases, because it is equal to minus n pi nu. The slope of this is minus n pi. In this case, it indicates that the phase is constant. So this is called as the constant phase property of FIR filter. And because the phase is constant for every q, when I take d nu of this, that is what I call it as the group delay will be constant. The phase change is constant for every sample, equal to pi n pi pi nu into q. So group delay becomes constant. So this is also called as linear phase FIR filter, and it has a constant group delay. This is linear phase characteristic that is being plotted. Now let us see what is the meaning of windowing and what happens because of windowing. So this is the impulse response existing between minus infinity to plus infinity. What I do is I just multiply it by the rectangular pulse train. which is existing between minus q to plus q. So between minus q to plus q, I'll get the response, and below minus q and above plus q, the response will be 0. This is how I truncate the response. So in truncating, what I'm actually doing is the impulse response is getting multiplied by the rectangular pulse train. So what happens in the frequency domain? This is a brick wall response that I expect. Now when I truncate, what happens is it gets convolved with the Fourier transform of the rectangular pulse, rectangular window pulse. And this is a sinc function. So what happens is the actual response that you get will have a ripple in the pass band, and it will have oscillations near the band edge of the filter. These oscillations near the band edge of the filter is what we call it as Gibbs phenomena, and this is occurring because of the truncation. Windowing of impulse response results in ripple in the pass band and oscillations in the stop band. The stop band oscillations are also called as spectral leakage, and the oscillations near the band edge of the filter are called as Gibbs phenomena. The oscillations near the bandage will have to be, or we would like to reduce it, and we can reduce it by using some smooth window function that will come to it in the next lecture. So how the filter design specifications will be given? We normally plot attenuation with respect to frequency graph. This is a pass band, so attenuation will be minimum, and there will be some small ripple in the pass band that can be tolerated. So tolerable pass band ripple will be specified. The pass band edge will be specified. Stop band edge will be specified. The difference between stop band edge and the pass band edge is called as the transition width. This will also be specified, and the minimum stop band attenuation will be specified. So when you want to say that design a low pass filter for me, you will have to give these values. A ripple in the pass band edge, stop band edge, transition width, and the minimum stop band attenuation will have to be specified. Then the user can design the filter for you. Now, FIR filter design using Fourier series expansion method, let us consider one simple example. Suppose the specifications are given like this. The response should be equal to 1 for 0 to 1000 hertz, and it should be equal to 0 otherwise. So, the sampling frequency is given as 8000 hertz, and the duration of the response is 2.5 milliseconds. Sampling frequency is 8000, so the Nyquist frequency will be 4000. So as compared to 4000, this 1000 is at 0.25. So this is the cutoff frequency. Now calculate the duration of the response tau. This is 0.0025 because 2.5 milliseconds. So I convert it into seconds. 2q into t. T is sampling interval. It is 1 upon fs. So I get q is equal to 10. So number of filter coefficients I'll have to design will be 10. And the coefficients will be 10 coefficients will be on the negative side, 10 coefficients on the positive side, and I will have the coefficient at 0. So there will be 21 coefficients. The filter will have 21 coefficients. Now how to calculate the corresponding filter coefficients? I'll have to use the equation 0 to cutoff frequency. Now this is 0.25 in terms of the normalized frequency, cos n pi nu d. Now, if I integrate this, I'll get sine n pi nu upon n pi between 0 to 0.25, and Cn can be written as sine of 0.25 n pi upon n pi, ranging between 0 to pi. So if I put the value of n as equal to 0, 1, 2, 3, etc., I can calculate all these coefficient values. So, but C1 will be same as C minus 1, C2 will be same as C minus 2 because the coefficients are symmetric with respect to 0, and obviously we'll be shifting it by q samples, and we'll be making this q minus 10 as equal to a0. We'll call this as aq, and we'll call this cq as equal to a of 2q. Now, if you write a MATLAB code for filter design, you will get the filter response coefficients like this. In MATLAB, the corresponding 0th number is, if you consider it is actually 1, but you plot it from 0 to 21, right? Now, this is the magnitude response plot. Magnitude response plot. Magnitude is almost flat up to 1000 as was expected. After 1000, that is the cutoff frequency, we are getting oscillations in the stop band. These are the oscillations, these are due to what we call it as the spectral leakage. You see that the attenuation is almost about 25 dB, minus 25 dB. And you see that the phase remains linear in the pass band, and after the stop, in the stop band, of course, it is not linear, it is varying, oscillating. So in the pass band, it will be linear. This is called a linear phase response.